Hey everybody, we are on day 2 of section 7.4 and we're going to go back over briefly about increasing, decreasing, strictly increasing, and strictly decreasing, and then we're going to focus here on how those particular things relate to the value of the derivative as we look at the relationship between the derivative and the original function's graph. Okay, so just as a recap from yesterday, because we did this briefly at the end, f of x is increasing, meaning it's generally going in an upward direction if f prime of x is greater than or equal to 0. Now, because of that equal to 0, it could have flattened off and become horizontal at some point, but at no point will it turn around and go down. Increasing means it's generally going up, although it could flatten off. Strictly increasing, you can see that there's no equal to there, so that means it's always going up. At no point will it level off and become horizontal. Similarly, with decreasing, it's going to be less than or equal to 0, so it's generally going down, although at some point it could flatten off and become horizontal because I see that it's equal to 0 right there. And then strictly decreasing, it is always going down. There's no equal to. At no point is it going to flatten off and become horizontal. So what we're going to focus on today is we're going to focus on these inequalities here. We're going to look at what happens with the derivative when f prime of x is greater than or equal to 0, or when it's greater than or equal to 0. Then the sign, let me switch, the sign of that is going to be positive. We're not going to have very many where it levels off and becomes equal to 0, but we could. So the sign generally when it's increasing, we're actually focusing more on this strictly increasing, is going to be positive. And then for decreasing and strictly decreasing, the sign there is going to be negative. And again, we're going to focus more on the strictly decreasing. We will have very few where it levels off and becomes horizontal. So in general, if the sign of the derivative is positive, my graph is going to be increasing, thinking of that in our minds as strictly increasing. And if the value of the derivative is negative, then the function is decreasing, thinking of that in our minds as strictly decreasing. Okay, so sign diagrams, we're going to spend today and tomorrow kind of building this idea so that you can really get it firmly in your mind. Sign diagrams are a method for determining whether the original function's graph is increasing or decreasing. So the sign diagram comes from the value of the derivative, but we are going to relate that to the graph of the original. So to complete a sign diagram, the first thing we have to do is find what are called our critical values. Two different places where we could have critical values. First of all, if the derivative is actually equal to 0, and in our sign diagram, we're going to use a solid line for that. So if the critical value is equal to 0, then that is going to, if the derivative is equal to 0, then that's going to be one of our critical values. Or if the derivative is undefined, if the derivative cannot exist at a certain point, then we're going to say that that is a critical value as well. And for those, we're going to use a dotted line. We're going to focus today on the ones with a solid line, and we're going to look tomorrow at the ones with a dotted line. Okay, so let's look at this one. F of x equals x squared. Okay, so the first thing I want to always do is find my critical value. So I'm going to take the derivative, f prime of x. All right, the derivative of x squared, that 2 is going to move down in front. And then for the new exponent, 2 minus 1 is 1. So 2x to the first, or just 2x. And now I need to look at where this is either equal to 0 or undefined. Well, this is a polynomial. Polynomials are never undefined, so I don't have to worry about that one. I just need to figure out where it's going to be equal to 0. So I'll set that equal to 0. Solving for x, divide by 2 on both sides. I get x equals 0. Okay, so let's graphically look at what's happening. Now remember, the graph that I'm looking at is the graph of our original function, not the graph of the derivative. All right, so here's my original function's graph, and you can see right here that when x equals 0, what I have there is a minimum value. Remember, we looked at the other day, my maximums and minimums occur when the derivative is equal to 0. So I have a minimum value on this. The derivative is equal to 0 at the point where x equals 0. Now I look at this side. On this side, my graph is decreasing. right? And you remember from yesterday and from earlier today, that means that it is going down, which means that the value of the derivative is going to be less than 0. I can see that this one is strictly decreasing. At no point does it level off. It just goes down all the way. Now on this side, my graph is increasing. And I remember from yesterday and from earlier today that that means that the value of the derivative is greater than 0. So when my function is decreasing, the value of the derivative is less than 0. Remember, we looked at all those little tangent lines yesterday. All those little tangent lines have a 0 gradient. And when the function is increasing, the value of the derivative is greater than 0. And we drew all the little tangent lines there, and they all had a positive gradient. Okay, let's look at this one. F of x equals negative x squared. Okay, so same directions. First thing I need to do is find my critical numbers. So I'll take the derivative. Negative 1 times 2 is negative 2. 2 minus 1 is 1, so I'm going to have that x to the first. Again, this is a polynomial, so there is no place where it's undefined, but I can figure out where it equals 0. This time I'll divide by negative 2. So again, I get x equals 0 for my critical number. And we talked about yesterday that when when the derivative equals 0, which in this case happens to be at the point where x equals 0, when the derivative equals 0, I have either a maximum or a minimum. Well, I see that there's a negative right here, which means my parabola is opening the opposite direction. So you guys can see right here at 0 that I'm going to have a maximum value. All right, so on the left-hand side of that maximum, my function is increasing, which means that the value of the derivative is going to be greater than 0. All those little tangent lines that we drew would have a positive gradient. The value of the derivative everywhere on this side is going to be 0. On this side, I can see that it's decreasing, so the value of the derivative is going to be less than 0. All those little tangent lines would have a gradient of 0. So if I were to draw a little chart, I could put x equals 0 right there. That's my critical number, and I drew it with a solid line. And on this side, the value is greater than 0. And on this side, the value is less than 0, right? Because in this side, it was increasing, and on this side, it was decreasing. Okay, so let's take a minute and write down some important facts as we move forward. All right, just some definitions that we need. First of all, a global maximum, also called an absolute maximum. A global maximum or an absolute maximum is the maximum value of y over the entire domain. So the highest that the graph goes over its entire domain. Not every graph has a global or an absolute maximum, but it might. All right, a global minimum is exactly the opposite of that. A global minimum is the lowest value of y over the entire domain. And again, a graph does not have to have a global minimum or an absolute minimum, but it might. Okay, so pause the video, write down those two definitions. All right, we're going to switch gears just a second. Instead of a global maximum, we also have what's called a local maximum. A local maximum is a turning point. You can see right here that it would be at the top of the hill. A local maximum is what some of the ones that we looked at yesterday, and the derivative is equal to 0 at that point. Opposite of that, a local minimum, well, that's at the bottom of the valley. And again, it is a turning point. I switch from being decreasing to increasing. In this case, I switch from increasing to decreasing. It's the opposite. And again, the derivative is equal to 0. Okay, so if we look at this graph right here, I can see that the absolute lowest point that this graph goes is here. So this is what we would call our global minimum. It is the lowest point of the entire graph. Opposite of that over here, that's the highest point of the entire graph. So that's what we call a global maximum. Again, you can also hear that called an absolute minimum or an absolute maximum. All right, now look at this point right here. This point is the top of a hill. It's not as high as this point over here, but it's higher than any point in its little area. All of these points near it are lower. It's at the top of the hill. So this is what we would call, oops, a local max. And then the opposite over here, this point is at the bottom of the valley. It's not as low as this point is, but it's lower than any point around it. These points are all above it. These points are all above it. So we would call this point a local minimum value. All right, so my local max, my local min are turning points. My global min, my global max are the highest or lowest that the graph ever goes. Now, if I have a graph, say, of a parabola, all right, let me draw a parabola in here real quick. Right, that parabola has a global maximum, and it seems to be the same thing as its local maximum, and there is no global or local minimum because it goes on forever. So that's what I meant by saying the graph doesn't have to have a global max or global min. This one happens to have a global max, but no global min. So that's a possibility, something just to kind of watch for. Okay, this chart I posted for you guys in Canvas. This is what we're looking at right now, local max and local min. We're going to focus more here tomorrow. We'll focus on that part of the chart. And look at what happens. When I have the local maximum, that's where my critical value is. That's where the value of the derivative equals 0. My local minimum, again, that's a critical value. That's where the derivative equals 0. We'll talk about that one tomorrow. And you can see on this side that the graph is increasing, so the value of the derivative is positive. Right here, the graph is decreasing, so the value of the derivative is negative. And then on this side, the graph is increasing again, so the value of the derivative is going to be positive. So basically what we're doing right now is we're just looking at the graph and we're learning how to draw this from the graph. All right, let's look at one more. Let's take the derivative of this one. So the derivative of this, 3 times 2 is 6, 2 times 3 is 6, and 12 times 1 is 12. There's my derivative. All right, that's a polynomial, so it's defined everywhere, but I can figure out where it equals 0. So I'll take that derivative, set it equal to 0. Okay, so those of you guys heading towards AP Stats next year, you're just going to type this in your calculator and you're going to find the zeros. Those of you guys heading towards pre-cal next year, you want to do this by factoring. So you're going to divide by 6 all the way across. And then you're going to factor this. Set each of your factors equal to 0. And I end up with -2 and 1 as my critical values. And if I look at my graph, well, here's -2 and here's 1. So this one is a local max. This one is a local min. This graph does not have a global max or min. And I can see that the value of the derivative here is going to be greater than 0 because my function is increasing. Right here it's decreasing, so that means the value of the derivative is less than 0. And again over here it's increasing, so the value of the derivative goes back to being greater than 0. If I put that in a sign chart, both -2 and +1 are critical values, so they are solid lines. And over here I said it was positive, and here it was negative. Right here, it's positive. And we said yesterday when it's increasing and then decreasing, it's a max. When it's decreasing and then increasing, it's a min, which matches our graph. Okay, so for homework, I want you to work on section 7.4, number 2. Do I and I, skip double I for right now. We'll focus on that some more tomorrow. So for I, find the derivative and the critical numbers. Put the graph of the original function in your calculator and then find the intervals from the graph in your calculator, looking at how they match up with the values of the critical numbers from your derivative. And then one thing to be really careful about is that f of x must be defined. Please take a minute, pause the video, and write this sentence down so you have that information. We exclude undefined points.